Right, in this video I'm just going to go over my ideas of how a car's electrical system works, and it's the kind of part 2 to my previous video, which was what to do if you have a strange or difficult to solve electrical fault. That was the first step on the previous video. This is what I would call the second step, and however, to understand the second step, which is very basic and very simple, really, what to do on the second step of a electrical fault, but it is important just to understand also the concepts behind the way the voltages uh, run around the car. It's probably the best way to describe it. Now, I've noticed here where I've got my cursor at the bottom, I've got like a picture of a field, and it's at 0 volts. Now your true 0 volts is the earth, the ground. Now the earth and the ground you touch is not electrically conductive. So what I mean is, if you live in a building, or you work in a building that's got like a lightning conductor and that embeds straight into the earth, that would be 0 ground. Or another way you can test for 0 ground, which is what I've done before in the past, is to run a extension cable out into your garage or wherever. Have a normal socket that you plug in to devices. Detach everything, detach all the cables, break the socket in half, unscrew it in half, plug it into it. Don't get electrocuted, of course. Plug it in. In fact, you could probably take out the two live and neutral prongs, take them out, and if you won't be able to do this in the USA because you do not have the earthing cable, earthing prong. What we do in the UK, in the UK, so if you plug your plug in to the socket with only the vertical. What I mean is, if you in the UK you have like a plug like this, you have two like that, two prongs, live and neutral, and then you've got like a prong. Is a very poor socket. This one here, that one is earth, right? And if you was to pull out these two prongs just for safety's sake, so they're not even plugged into the socket, but leave this one. If you used to test, that would be your true ground, right? Because that's going back to the ground, or the factory, to the power producing plant, whatever you want to call it. What do you mean by that, you would say? Right, what I mean by that is, if you was to test the negative terminal battery, if you was to use a multimeter, put one prong on the negative terminal battery, and I've done this before, and then one prong onto this. So if you used to connect here and here up, should switch to a different colour, with a multimeter, you would find that there is a little bit of a voltage, right? So on the negative terminal battery, you would find there is a volt or two, right? So between true ground and the negative terminal battery terminal. Okay, right. So in this kind of idealized diagram, it's not perfect. I'm not saying it's perfect. Don't come back to me saying that won't, that's not perfect. That's not connecting. I'll point out the bits I know are not perfect, but it's just an idealized thing. Let me just get rid of this. Right. If this is an example where the car is running, alternator is working. But saying that, in my example, the alternator is kind of on its way out. It's kind of, what I mean by on its way out is starting to fail because it's not producing a lot of voltage. So one end of the, and again it's idealized, the alternator is producing, and all the voltages I've shown here are relative to the 0 volts on the true earth. I've done that deliberately, just to point that out, really. So you've got 14.5 volts produced, right, on the alternator relative to the true earth of the ground, earthing of the ground. If you was to, as with the engine running, if you was to now test using a multimeter between the two terminal batteries of the battery, you should get 13.5 volts. Because if you're getting 14.5 here and you've got 1 volt here, remember I said there's 1 volt relative to the earth, and you're producing 14.5, you should get what you call potential difference, because that's what really a multimeter measures, is the difference of potentiality, electrical potentiality between whether it's measuring. So you should get the subtraction of 13.5 volts, right? If you was really doing this and you was testing with the engine on there, everything running, you had 13.5 volts, it really means that your alternator is on the way out, or on its last legs, because it's not producing enough voltage. You should be looking for something like 14.6 or 7, right? Where 14.6 is probably ideal volts. You are a couple of volts over, 2.1 volts over what the normal battery, which is 12 volts, right, is holding. So you are, with that extra 2.1 volts, you are going to be charging your battery, because you've got more oomph coming in than what the battery can take, if you know what I mean. So you imagine you're trying to stuff over the top here. Remember I also said it's analogous, electricity analogous to water. Imagine you're trying to, that's why I've done it in this way, this drawing, where the higher voltage is at the top, lower voltage at the bottom. I've kind of, it's not perfect, like I said. Imagine you tried to stuff a pillow. Let's say you're stuffing a pillow and you're stuffing things in. The more you stuff in, the harder it is to stuff the pillow, right? That's pretty much what it is. So if you imagine you use the force of only 12 volts, let's say, to stuff this pillow, and the pillow was resisting with 12 volts, because that's what's already on the inside the battery, or analogously the pillow, you will not be able to stuff any more stuffing into the pillow, right? It won't go. It will not go, because you're meeting equal force with equal force. You don't want to put any more stuffing. However, if you drove it up to 14.5 volts, you're stuffing. You can add more into the battery. So yes, you will be charging the battery. So that is why the alternator is a couple of volts above the battery's recommended design for voltage storage. However, of course, when we switch off the engine, or the alternator was broken, let's say, the battery would drop down. It would drop down to something like 12.5 volts. So, in our example, say 12.5 volts, but it's still enough voltage to run things. Okay, so the red line here at the top, that's the high voltage, and I've got the high voltage circuits like your starter motor. What else would be high voltage? Of course, the alternator would be in the high voltage. It's producing the power. So some of the pumps may be run on the 12 volts. Can't think of anything at the moment, but some motors may be driven on the 12 volts, right? So what to do in electrical fault, part 2. Okay. If something is faulty, right, as I said in the previous video, try and fix all the little light bulbs and things like that. If that's not working, you got to go to part 2. So in red, you've got the higher circuit. Try as an explanation. You've got higher circuit stuff running off the 12 volts, let's say, and you've got the lower circuit stuff running off the 5 volts. So notice I've got the 14.5 here. 14.5 subtract 2 is going to give me 12.5. So 12.5 volts, right? I've got all these components running on. So imagine it's a flow of water. You've got more oomph at the top. It's pushing through the components, and it's this bit that, of course, it's not going to go through the components. If it could run along the side. It will a little bit will run through the component, but it shouldn't do, right? It will run along the side. I know it's not perfect, but I know that. And the same with the low voltage circuit, but I'm just drawing it as like an idealized thing. So you've got these components in there, on the high voltage, and then in the yellow rectangles, that's what I'm calling a relay. But of course, it's not. I'm not drawing it very well. I've only connected one relay up, and of course, again, like I said, it wouldn't run through here if it could run. It wouldn't run through this fuse. Oh, that's my fuse. It wouldn't run through the fuse if it could run alongside. Of course. No worries. But it's basically a relay is like it's probably what size of your thumb, and it's like rectangular cuboid, right? In there, you've got an incoming 7 volts control, and then 2 volts coming out. That's why you normally have 4 prongs on there, right? So you've got like a control circuit, which is connected to your buttons in your car. If you, for example, wanted to switch on, good example, windscreen wipers, right? If you want to switch on a windscreen wiper, is that a good example? What I need to say it's definitely 12 volts. I think windscreen wipers are 12 volts, and don't point me on this, because I think it's got to have a lot of power in it, so the 12 volts makes sense. Windscreen wipers are very powerful, right? So you've got the control circuit running off 5 volts, so 7 minus 2 is 5. What that means is, if, for example, and of course there'll be a switch in there somewhere. Let's call that a switch. Call that thing a switch. The switch will be your button that you're pressing in the car, right? These days it wouldn't be a physical button. It would just be a kind of in most cars it might not be a physical button. It might go to the computer first. But anyway, just pretend it's a physical button from the old days on normal cars. Press the physical button, close the circuit, runs through the fuse. Once it runs through the fuse, it creates a magnetic field inside the relay. So what happens is it flips a second switch inside the relay here, and that's when that switch closes. Now you're closing the circuit between the thing you're going to try and run, and let's say the windscreen wiper motor. I just can't think of anything that's 12 volts. What did I say? Something's going to be 12 volts. Starter motor, of course. Starter motor, right. You flip that switch and the circuit is completed. So now you've got the difference here is 12.5 volts running through. So you run that component, right? So what a relay basically does is it offers you as a user an opportunity not to electrocute yourself with high voltages or high currents, because running through the 5 volt circuit is not high current, it's low voltage and low current, and it offers you, and the relay is the thing that's the between you, your low voltage and your high voltage, right? That's why I put it in between these two. You run your components, it drops down after it runs through your component. Your voltage drops down to 2 volts where it meets the chassis of the car. Same thing with your control circuit. Your 5 volts drops into the chassis of the car, the earthing point. These are you'll have two. It might have this. It should have 2 different earthing points, right? Ideally, otherwise there'll be an issue with high voltage and low voltage. In my opinion. Right. Okay. So the electricity runs through your car, and then it drops back to the battery. So I've got 2 volts relative to the ground. Don't forget on the chassis, and 1 volt relative to the ground on the battery. So it runs through, drops another volt, drops 1 more volt. So it goes down another volt. Into the battery, back into the battery, right? Okay, so that is how things should run. It's a bit like flowing water. Things higher up will flow into things lower down in water, or what you call gravitational potential energy. Things that have higher gravitational potential energy will drop to lower gravitational potential energy. Otherwise, water won't flow, even if there's a slight dip in the ground, water will flow. Same with electricity. That's why when some things are broken, some things are blown, like a certain bulb, you like I said in the first video, part 1, you're going to have all sorts of odd things happening, like the electricity won't flow properly, because you've got higher voltage where it shouldn't be high voltages, as a simple explanation. Right, so in part 2, when the key thing is when you have when you have an electrical fault and you've eliminated, like, there's no light bulbs blown or anything like that, you've got to look for the fault. Okay, sometimes there could be like a break in there. I just want to change colour. So sometimes there's a break. I'm going to make it thicker. Sometimes there's a break in the circuit here, let's say, or a break in the circuit here. Right. Sometimes, quite often, the earthing points are dodgy. Okay. They're not conducting electricity very well, so they need to be cleaned. Sometimes it could be that. So whenever you open up your car, if you see rusty earthing points, clean them. Right. Take them out, and make sure the battery's out. Clean it. Put it back. Make sure it's good earthing points. It could be like a break here, a break here. These need to be fixed. Okay, you can locate them. If it's a break here and a break here, you can have whole swathes of things not working. Right, so the whole electrical system of your car may not work. Or if let's say one earthing point was so rusty that it wasn't working, you would lose so much, and the electricity may try and reroute itself. Maybe it might try and reroute via another component or via the engine or whatever it is to try and reroute itself through there. This is where you can have problems coming in. Electricity trying to go into this earthing point, and let's say for example this was, I don't know, 2.1 volts coming in, and this was 2. You're gonna have a problem because it's going to try and get back into this circuit. It will stop this one flowing. Or it'll be all sorts of odd things happening. So electrical faults can be very, very difficult. However, the second step, well, I can't really mention the third step. This looking for breaks is really the third step, and that might be another video. I might do a practical on that if I get a chance. However, the second step is a bit easier than that. What you should be doing is looking for broken blown fuses, right? You may fix the thing that's happening, maybe not the cause though, but it could be a blown fuse, so a fuse may need to change. It could be something blowing the fuse, could be all them light bulbs blown, sending too much current through that fuse and blowing it. It could be things like that. So make sure you do step 1, fix all the broken components, simple ones like light bulbs. Or it could be more commonly that, okay, it could be the relay. The relay could just be worn, because that's the only moving part, apart from the things that are actually moving, like the start motor. That's a moving part in there. They do get worn out, right? So it could be the relay or it could be the fuse. Check the fuse first. Next step, check the relays. Hear it clicking. Sometimes even if it clicks, still doesn't work. Doesn't mean it's working. May need to swap it or buy a new relay to check. See if it runs your component. Now, if your component, let's say start motor, still doesn't go, obviously there's a step 2.5. Step 2.5 is change the component, of course. Alright? But anyway, enough said on that. It's a complicated things. One of the more complicated things, especially in old cars, when we know the earthing points are going. It's just so annoying when you have electrical faults. You could scrap a car. People could scrap a car with just because of a rusty earthing point, and you could just literally 5 minutes take it apart, it's great, put it back there, and the car will run perfectly. So work on it, guys. Work on it. This is my personal take on what's going on when you have electrical faults, and to this day, it still serves me well. My theories on it. All right. Thanks for watching. Good luck with your repairs.